All right, section 5 is all about friction. So if you haven't caught on yet, we're kind of going through all of the forces that we were talking about back in chapter 4, one by one, section by section. So here is section 5. We're talking about friction. Friction is actually everywhere. We spend a lot of time ignoring friction on problems, but we actually have friction all over the place. Without friction, we wouldn't really be able to do anything. We'd just be kind of trying to move, and we would never be able to. So it actually is everywhere. We previously talked about the static friction force as F sub S, and that is the force that, this should be a surface. I just have typos all over the place because when I was typing these notes, it was very late at night all the time, so that's why I have these typos. Anyway, a surface exerts on an object to keep it from slipping on that surface. As long as the object does not move, pushing or pulling harder means a larger static friction force to balance the forces in that direction. So there's supposed to be a picture here, that's why there's a colon, and the picture is actually on the next page for me, so here we are. And so we have this force identification. Remember, force identification is the actual drawing of what's going on, and then we have the circle around the object, and then kind of the forces that are acting. So we have this lady here pushing on whatever this like cardboard box is, or refrigerator, or whatever. And then we have the weight down, and then we have the normal force up. We have the force of the push. So the lady is pushing in this direction, which means the friction force would be acting opposite of that motion. Okay, if the object was in motion, it would be moving to the right. So the friction force would be acting which way?
To the left.
Yep, to the left. So it's going to resist the motion of the object if it was moving. So the friction force would be acting opposite the direction of the push. So in the free body diagram down here, we have the weight down, of course, and then we have the normal force up, of course. Those are counteracting each other. The object is not going up or down. And then we have the force of the push to the right. So the friction force is to the left, opposite the direction of the push. The object is not moving, therefore the F net must be 0. So that completes the free body diagram. Okay, any questions on that?
Yes.
All right. So there is a limit to how big the static friction force can get, and that is because the object eventually, if you push hard enough, is going to begin to slide. So once the object begins to slide, or right at that moment I should say, the breaking point where the object would begin to slide, we're going to call that limit F sub S max, the maximum static friction force. This force is proportional to the magnitude of the normal force between the surface and the object. So let me kind of scroll up a little bit. That means this. F sub S max equals this new symbol right here. That is the Greek letter mu. It has a long front, and then it's like a U. That should be connected. There we go. That's the Greek letter mu sub S. And then the N is the normal force. So that's F sub S max. Now this mu is something new. We just need to know what that is. This equation does not say that the force of static friction is always mu sub S n, just that the maximum static friction force is that value. Okay, that's the breaking point where the thing starts to slide. So F sub S can be anything between 0, when I first start to lightly push, and F sub S max. So the rules for static friction is always a direction opposite to the motion that it would be going if it was in motion. The magnitude always adjusts itself so that the net force is 0 and the object does not move. And the magnitude can't exceed the maximum value F sub S max. Otherwise, if it does, the object will begin to move. All right, so we continue. So that was static friction. Now we're going to talk about kinetic friction. So once the object begins to slide, so we broke through that F sub S max, and now we're going to begin to slide. Static friction is now replaced by kinetic friction. So that's a sliding friction force. We call it F sub K. That force is still always opposite the motion. So it's in the same direction as the static friction force, which is opposite the direction of motion. We are now in motion. It is going to be nearly constant in magnitude, and it is given by this equation right here, F sub K equals now mu sub K times the normal force. So it's like we built static friction force until we got to the maximum static friction force, and we broke through. And when we got to that maximum static friction force, it was almost the same formula as this right here. But then it's actually, that static friction force actually is a little bit greater. We don't know that really. I'm just kind of going into a little bit of an aside. The maximum static friction force is actually a little bit higher than the kinetic friction force. We'll talk about that later. The magnitude of the kinetic friction does not depend on the speed of the object. So as I kind of said here, it's nearly constant in magnitude, so we can speed up and the kinetic friction force is actually going to remain kind of the same. And we can see that here in this formula. Mu sub K is a constant. By the way, mu sub S is a constant also. That's a property kind of intrinsic to the material that you're dealing with, times the normal force. And the normal force isn't really going to change much depending on the kind of the weight of the object, right? I guess if the angle that you're dealing with changes, then the normal force is going to change, and that will change the value of the friction force. But that's going to be about it. The speed of the object is not in this equation anywhere, so that's not going to change the magnitude of the friction force. Anyway, the magnitude of the kinetic friction does not depend on the speed of the object. We have in this table right here, table 5.2, it says the coefficients of friction. So I'm giving you some stuff here to kind of reference back to. If you have some homework problems that are asking you for a mu sub S or a mu sub K, you'd want to reference this table. So rubber on concrete, so this would be like if you have tires that you're talking about, you'd want to reference rubber on concrete. Steel on steel, rubbing, if you had, so like some sort of steel cabinet sliding on, I don't even know, steel rails or something like that, then you would have that situation, okay? Steel on steel lubricated, so that would be like if I had oil in between these two steel parts that were rubbing, then you would be looking at this one. Wood on wood, if you had wood on wood that was being pushed, so a wood block trying to be pushed on another wood block or something, you would use this one. Wood on snow, so if you had like a wooden sled or something and you were trying to push a wooden sled but it wasn't moving, or then it broke free and it was moving, then you would use that. A block of ice on another, like a skating rink or something, then you would use this, okay? So this chart is going to be referenced for problems that would involve these guys, okay? Now notice how the static friction changes. So we have the static friction here changing to kinetic friction as it starts to move. Notice how the static friction is always higher than the kinetic friction. So rubber on concrete, if we are just moving without sliding, so we're not spinning our tires, the static friction is 1.00, but if we start spinning our tires, then the static friction, or the kinetic friction, becomes 0.8, okay? Now notice how I said that. We're just rolling, like we're moving with our tires, but then we start spinning our tires and we have 0.8, okay? Now, if we're rolling, this is a little bit different, okay? So static friction, I'm trying to push my tires, so that would be sliding. Now I'm spinning my tires, so now they are sliding. Now I'm rolling my tires, like rolling the wheel down the road. This would be a little bit different. I have 0.02, okay? So now steel on steel, if I have some sort of steel and I'm pushing steel, that I'm trying to push that steel, 0.8, and then I'm actually sliding that steel, it drops down to 0.6. Now if I'm rolling steel, so I have a steel ball rolling on steel, it's 0.002. So if you guys remember when we did that track, we had the steel ball rolling on the steel track. It was actually aluminum, but it's basically the same thing. Notice that the friction was actually very, very low here, okay, which was why we were allowed to do what we were doing and estimating the speed as being pretty constant the entire way. If we had oil on that track, it probably would have been even lower. Okay, so just continuing to point out more of the difference, the drop between static and kinetic. Wood on wood, if I'm trying to push wood on wood, we have 0.5 for static, but then once it gets moving, we have 0.2 for kinetic. Now, physically, if you've ever tried to push something, it's generally easier or harder to push something once it gets moving. It's easier to push something once it gets moving. And if it stops, you're like, oh God, now it stopped, I gotta get pushing again. And then once it breaks free, it's always easier and you want to keep it moving, okay? And this is kind of reflecting that idea. The static friction force is higher than the kinetic friction force based on these coefficients of static and kinetic friction, okay? So physically you should kind of be understanding where these numbers are kind of coming from, even though you don't know why these numbers are what they are. Okay, so now rolling friction, we kind of talked about in that chart, but we don't really know what rolling friction is. So here we are. When you're driving, if you slam on the brakes and the wheels slide on the road, that's kinetic friction because we're sliding. The wheels are now skidding. But a wheel rolling on a surface is actually experiencing something called rolling friction, and that is F sub R. So we have F sub S for static friction, we have F sub K for kinetic friction, that's sliding. And we have rolling friction now, so that's F sub R. And we have a formula for that too. We have a mu sub R, so that would be the coefficient of rolling friction. That is a number, just like mu sub S and mu sub K. And that's times the normal force as well. So this type of friction acts a lot like kinetic friction, but it has a much lower value than mu sub K because it's much easier to roll something than it is to slide it. If you can roll the object, it's easier than it is to slide the object. And probably physically you know that as well. So let's rank in order from largest to smallest the size of the friction forces F sub A through F sub E in the 5 different situations. And one or more of these forces could be 0. The box and the floor are made of the same materials in all situations. So we can take a look at this. Think about it to yourselves for a little bit, and then we'll compare our answers and come up with what is actually right.
I got caught up in the weeds and
So we're saying B is, F sub B is the biggest one because it is on the verge of slipping, which means it's not moving, so it has a static friction force, and it is the only one that is not moving aside from the one that's at rest. But because it's at rest, there is no friction force to talk about because there's no push at all. If we have no push, we have no force, and there's no force to resist it, so then there's no friction at all. So way over here, I'm going to put F sub A. Okay. So now we have to talk about C, D, and E, because they're all in motion. They all have a kinetic friction force, which must be smaller than the static friction force. So how do we arrange C, D, and E?
C would get F sub A because I'm speeding up what's going to push you on the less because if you look at something, if you body like then the push is getting stronger and the force and so you know what I mean?
So when I looked at the rest of them, I was immediately struck with, I thought they were all the same. But I mean, given the way the question is worded, it's probably wrong. But I think they're the same just because kinetic friction is a constant, and it's the constant throughout all the things. It doesn't matter what speed you're going, it's constant. Since the box is made out of the same material.
What do you guys think about that? The magnitude of the kinetic friction does not depend on the speed of the object. Does that help?
Well, the only thing that's slowing it down is the friction force. The other opposing forces, like the constant speed one, it has that force,
I think at easement.
that force opposing.
You think what?
At easement.
Yeah.
Your acceleration. Your acceleration. But then I also have.
The magnitude of the kinetic friction does not depend on the speed of the object. Does that help? So if the magnitude of the speed of the object, or if the magnitude of the kinetic friction does not depend on the speed of the object, then the magnitude of the kinetic friction is what? No, constant. So, we have kinetic friction in C, D, and E. It is what?
The same.
The same in C, D, and E. So that means F sub C equals F sub D equals F sub E. They're all the same. Doesn't matter what direction it's going, it doesn't matter how fast it's going, it doesn't matter if it's speeding up or slowing down. The kinetic friction force is the same in all three. Okay, that is a very important point. You need to know it. The static friction builds as you increase your push or decrease your push to keep the net force zero until you reach the breaking point, and then you break free and you switch over to kinetic friction, or I guess rolling friction. But once you have kinetic friction, the kinetic friction force is constant.
So I noticed on the equation, friction is a constant, and it's also multiplied by normal force, which
Yep.
is just weight in the, well, it's weight in the y direction, but positive.
Yeah. So yeah, if you're at an angle, then the normal force won't be just weight, right? It'll be some kind of,
Yeah, weight,
yeah, depending on if you're at if you've tilted your axis.
Yeah.
So watch out for that. Okay, you want to move your couch to a different room. You place sofa sliders, which are slippery discs with a mu sub k value of 0.080 under the feet of the sofa. You then push the sofa at a steady 0.40 meters per second across the floor. How much force do you apply to the sofa? What do we do?
draw a picture.
Okay, you want to draw a picture? It's not necessary to draw a picture?
I think it is.
Well, we could draw a picture. We could have a lot of fun drawing our picture. So here's our sofa. Amazing looking sofa. And then here's us. Very happily pushing our sofa along. Which way are we pushing our sofa?
That way. The way that your arms would be pointed.
Okay, so our force is going this way.
Want to draw the surface slightly?
No. Which way is our friction going then?
The other way.
Okay, so friction is going this way. That would be F sub what?
Okay.
Okay. It wants to not draw the K. There we go. All right, and yeah, sure, we can draw the sofa sliders. Those are little hockey puck looking things. Okay, what else do we have going on in this picture?
Weight and normal force.
Okay, so we have a weight down and a normal force up. Ooh, that was up. All right. What do we know?
We know the friction, and we know the force applied.
We actually don't know the friction. We know mu sub K.
Oh yeah, which is the constant, therefore the coefficient too.
The coefficient of kinetic friction is 0.080. And we know the velocity initial, which is the same as the velocity final because we're pushing at a constant velocity, which is 0.40 meters per second. Okay, so what should we do now?
Let's see here. We're looking for force, right?
We should probably draw a free body diagram.
Yeah.
Okay, so here's my sofa. I have my applied force to the right. I don't know what it is.
What did you push?
It is a push. I have my F sub K to the left. This should be exactly the same length as my applied force because I'm pushing at a steady speed. I have my weight down, W, and weight we now know is exactly mg. And we have a normal force up. And those two things should be exactly the same as well. And we have an F net of what? 0. Okay, so there's our free body diagram. There is a piece of information missing in this problem, which causes a problem. We wouldn't be able to solve it if we didn't know that our sofa doesn't weigh, but it has a mass of 30 kilograms.
I was looking at it and I was like, huh?
Yeah, I kind of left that part out. Again, late at night when I typed this up. So, what do we do now?
So now that we know the,
You need to solve the normal force. And the final
We need to do a sum of the forces. Sum of the forces in the y direction would be what?
so it'd be N or weight.
Sure,
N
n is positive,
minus W.
minus the weight, and
Zero.
equals 0 because these are in balance. Now I can solve that for the normal force. N equals the weight, but the weight is mg, so I'm going to say N equals mg. Okay, sum of the forces in the x direction. What do I know?
So F sub K.
So I have a positive F minus F sub K.
F sub K equals F.
Equals 0 first.
Yeah.
And then I know that F sub K, because this thing is moving, so like off to the side, F sub K is the formula mu sub K N. But N equals mg, so I can substitute in mg for N. So F sub K equals mu sub K mg. So F sub K equals mu sub K mg. So now back into my sum of the forces in the x direction equation. If I solve this for capital F, F equals F sub K. So now I can substitute in for F sub K, and I have F equals mu sub K mg. I know mu sub K, I know m, and I know g. So now I can solve for F. F equals, the mu sub K is 0.080. That's the coefficient of kinetic friction. The mass is 30 kilograms. And G, of course, is 9.8 meters per second squared. So what is the force that I am applying to get the sofa across the floor?
$23.
23 point something, 5? Okay, so significant figures.
So 1, 2, 3.
This only has 2,
Oh,
so 24 newtons. Okay, so in this problem we had to use both some of the forces in the x and y direction in order to get our way down to what the force was. Alright, so a lawn roller, if you've ever seen one, it's basically a heavy cylinder. Sometimes they're just fully concrete, sometimes they're hollow and you fill them with sand or water. Used to flatten bumpy lawn. If you're doing landscaping, you would use this. When I redid my lawn, I had to use one. Is it easier to push or pull a lawn roller? You need to think about it for a minute, probably.
that's all.
So we have two scenarios, right? We got a push and a pull.
And this is F sub R, right?
If I do
This is the long roller.
a free body diagram for the push, I'll have the weight down, the normal force up. I'm going to push, so I will have a friction for, I'll have the push, but the push will be directed to the right, but also down because I'm pushing on this roller.
Oh!
Okay. I'll have the friction force backwards.
So like,
I'll have the weight down and the normal force up, but I'll be pulling this time, so I'll have on the handle, I'll be pulling to the right, but also upward. I'll still have the friction force backward.
I guess I just didn't know what a long roller was.
I'm confused on lights.
Think of a lawn mower. It's the same thing,
Oh,
But it's real.
but it rolls. Same idea,
So how come it's going to the right?
because that's the way I decided. Think of a lawn mower. You ever push a lawn mower?
Yeah.
You're pushing in the direction that you're going, but you're also pushing down on the bar. Okay? Same thing. Or I could pull. I'd be pulling in the direction that I'm going, but I'm also pulling up on the bar.
Probably that's the same way.
Okay. So now, which would be easier to do and why?
It'd be easier to pull because you're not forcing it to the ground.
Okay. So not forcing it into the ground is a good way to put it. Here I'd break this into components and I'd have a component of push down and I'd have a component of push this way. Now the component of push to the right is going to be what the friction force is coming from, but the component of push down is adding to the weight, which is going to add to the normal force, which when I'm dealing with friction force, the friction kinetic is going to be mu sub k times the normal force. And if I just added to the weight here, I'm adding to the normal force here. So that means I'm increasing the kinetic friction force, which means I am making it harder to push. Here, I am going to have a component in the pull direction, but I'm also going to have a component where I'm actually lifting up a little bit on the weight of the object. So I'm actually reducing the weight on the object a little bit because I'm pulling up, which means I'm actually reducing the normal force that the ground is pushing back on the object. So when I'm looking at this formula here for the kinetic friction force, Because I reduce the weight, I reduce the normal force, which means I'm reducing the friction force as well. So therefore, it will actually be feeling a little bit easier to pull. Okay? So that's why. It's easier to pull than it is to push the roller or the lawnmower or whatever. So kind of an interesting result there.
You know what, next time I mow my lawn, can you get up to the floor, I will pull it, and what kind of says what the hell I'm doing, it's all physics.
Physics, yeah, that's all. Let's just say that, physics. Okay, so now we have a 50 kilogram steel file cabinet on the back of a dump truck. The truck's bed, also made of steel, is slowly tilted. What is the magnitude of the static friction force on the cabinet when the bed is tilted 20 degrees? At what angle will the file cabinet begin to slide? So it's a two-part problem. What do we do?
Draw a picture.
Okay, we draw a picture. So we have our dump truck at a 20-degree angle. We have a file cabinet. Sitting on the dump truck. That's a pretty good file cabinet. Know exactly what that is.
Beautiful.
Yep. I know. All right, what do we do? Free body diagram? Okay, great.
How much did you keep it wrong?
How should I draw this free body diagram? Tilted axis. Okay, so I have my file cabinet. That's my free body. What's going to go on here? Okay, so my tilted axis of 20 degrees. The weight though is still going to be directed down, right? So here's my x-axis. So here's my y-axis. X is positive down. So weight will be directed which way? Directly straight down towards the center of the earth. There's weight. Weight is mg. Now what?
The normal force is going to be directly along the line.
Normal is directly along the y-axis. So in the negative direction along the x-axis, this would be F sub S. The file cabinet is not moving. 20-degree angle. Where?
But if we made a split, wait, split it if we use the 20.
Oh, okay, we can do that. So the weight vector is split. We have a weight along the y-axis, so W sub y, and a weight along the x-axis, so W sub x. So where's that 20-degree angle? Between W sub y and W, okay.
So the angle, the weight, when is it okay, and then we can do, what is that? That's adjacent, hypotenuse adjacent and cosine, right?
No.
That's that.
What do we know?
We know the weight of it.
Where did you find that? In the table that you got earlier, we know the static friction coefficient. So that would be mu sub s in this situation. You said was what? 0.8? Just 0.8? Wasn't 0.80? Oh, we want that then. We have the mass, 50.0 kilograms. Anything else we know?
The angle, but it's in the picture.
Yeah, we know the angle.
Gravity.
We know gravity.
You don't have to write that down.
Okay. That good? Okay, what are we looking for?
At what angle would this line?
The magnitude of the static friction force.
Oh, yeah, what's my picture?
So we're looking for what?
Static friction.
F sub s for the first part. And then for the second part,
The angle in which the cabinet begins.
so this is a totally different problem then. We're looking for theta in a totally different way, all right? So that would be like a second free body diagram even. We're gonna have to redraw it. So we'll deal with that in a minute. All right, so let's see what we can do here. What do we need to do?
Well, first off, we need to cosine, we need to figure out W sub x, so we can figure out normal force, so we can figure out static friction.
Okay. So W sub x,
Okay, W sub y.
W sub y.
Yep, I meant that, yeah.
Okay, so if I complete this right triangle right here, what are we dealing with?
Cosine.
Cosine, okay. So we would have cosine 20 degrees equals what?
Weight WY over W.
Over W. So then we would have W sub y equals W cosine 20, but W is actually mg, so I'm going to write mg cosine 20 degrees. We know the mass, we know g, we know cosine 20 degrees, so we'd be able to figure that out. Okay, what do we do now?
Why don't we take the F sub s equals mu sub s times.
How about we do some of the forces in the y direction? Always do this. Some of the forces in the y direction would be what? The normal force is positive. W sub y is negative. So n minus W sub y. And what do we know here? Equals 0. How do we know that?
This is not moving.
This is not moving. We needed to write F net equals 0. So n equals W sub y. So that means n equals mg cosine 20 degrees. Okay, so what can we do now?
If you want,
I want to do the,
so F sub s, F, no, wait. F sub s equals mu sub s times n. right?
No.
No. Oh, wait. Wy equals n. Or, yeah, right?
Wy equals n, yeah, we have
Yeah.
that.
So we can substitute Wy or n in for Wy on that equation, right?
When do we solve for n?
We did solve for n.
F sub s is equal to, mu, that,
No. That is not an equation. We don't have that equation. That equation only works for F sub s max, and we're not looking for F sub s max.
Oh. But then how are we supposed to figure out the... We can do some of the forces in the x direction.
All right, some of the forces in the x direction.
Figured it out, Cole. Figure what he wanted us to do.
Equals what?
Wx minus f sub s equals 0.
Minus F sub s equals 0. By the way, what are we looking for?
F sub s.
Oh, So then F sub S equals W sub X.
Oh, silly little me.
How do we find W sub X?
We can figure out that, well, since that's a right angle, 90 minus 20 equals 70, so that angle
Why would you do that? Why not do sine 20 degrees equals W sub X over W? So W sub X equals W sine 20, but W is mg sine 20 degrees. We know m and we know g, so we have F sub S equals mg sine 20 degrees. We should have done that all along.
Would you let us?
Yeah, always do your sum of the forces and remember what you're looking for.
So we didn't have to do.
No, we didn't. Okay, so M is 50 kilograms. G is 9.8 meters per second squared. Sine 20 degrees. What do we get? Okay, so significant figures would make us 168. What? Newtons.
We have to figure out the other.
Now, at what angle will the file cabinet begin to slide? Now, begin to slide means we've reached our F sub S max.
That's when it's coming back.
Now we can use F sub S max equals mu sub S times n, and we have n equals mg cosine 20 degrees. Now we can use this idea here that you were trying to use. We could not use it before though, okay? So, we did not waste time doing what we were doing. We just were headed in the wrong direction for the first part. So, F sub S max, F smax is mu sub S times the normal force, but the normal force is mg cosine 20 degrees. Right? And mu sub S is that 0.80. So what do we do? It says, at what angle will the file cabinet begin to slide? So we're actually not looking for F sub S max, we're looking for the angle. So we're going to have to do a little bit of extra work. We'll have to figure that out next time.
Yeah, Vinyana.